Hey, this is Ken with My Math Assistant, a website that I created as a companion for the Saxon Math curriculum to be used in schools and homeschools. I just wanted to talk you through real quickly some of my strategies and approaches to these problem-solving questions where we have missing digits. And these typically show up, I've seen them in Math 6.5, Math 7.6, and Math 8.7 especially. They typically show up in the mental math and warm-up sections. And I've had a few people ask me, how do you solve these kinds of problems? There's not really teaching that I can see in the Saxon curriculum for how to go about the approach and how to go about solving these kinds of problems. So I just wanted to talk you through some of my strategies and approaches that I use with my kids because they often bring these questions to me as well. They're completely stumped, which I totally get because they're pretty difficult problems sometimes. So here's how I approach them. The first step is observation. The second step is typically elimination. I start by just observing everything I can note about that kind of problem. So for example, this first factor for a multiplication problem has 3 digits in it. The second one has 1 digit. And finally, the product has 4 digits. So that's one thing I would observe right away. I would also observe that this is an odd number. Now, when I think about what I know about multiplication, an odd times an odd equals an odd. And if either of the factors are an even number, then the product is also going to be an even number. So I can actually eliminate all even numbers, at least for the 3-digit number here and the 1-digit number. These have to be odd numbers, which means this has to be an odd number, and this has to be an odd number since every odd number ends in an odd number in the ones place. So now when I think about this number right here, I'm eliminating some of the numbers. I'm kind of on this elimination step already. I've already eliminated all the even numbers, so the only possible numbers that could go in that spot are 1, 3, 5, 7, and 9. So let's just walk through these 5 numbers and see which ones we can eliminate. Well, if I take the number 1 and I put it here, I can see that won't work because if I take a 3-digit number and multiply it by 1, I would expect to get a 3-digit number down here because multiplying by 1 doesn't change the value of this number right here. So I can eliminate that right off the bat. This can't be the number 1. Then I think about my rules of divisibility, and that may be a lesson that's in your book that you could look up. So some of the rules of divisibility, for example, I know if a number is divisible by 5, then it will end in a 5 or a 0. So this can't be a 5 because if this number right here was multiplied by 5, then this would have to be a 5 or a 0. So I can eliminate 5. I also know that if a number is multiplied by 3, then all of the digits of the resulting product will also add up to a multiple of 3. Now the digits of this number add up to a 2, and a 2 is not a multiple of 3, of course, so I can eliminate 3. This number right here cannot be a 3. The same rule applies for 9. So if I multiply a number by 9, then when I add up all the digits of the resulting product, those digits should also add up to something that's divisible by 9. Well, 2 is not divisible by 9. Therefore, I can eliminate 9. Now you can see what we've done. We've actually eliminated every single digit that goes here except for the number 7. And that's really the hardest part of this particular problem. Once I get a 7 here, I can actually just divide 1001 by the number 7, because now we have a multiplication problem with a missing factor, which ends up being a division problem. So we take 10 divided by 7, subtract 7, we get a 3, bring the 0 down. 30 divided by 7 is 4. 4 times 7 is 28. I subtract and get a 2. Sorry, I'm running out of room. I bring down the 1, and 21 divided by 7 is 3 with no remainder. So this number right here is 143, and the problem solved. So I started by just observing everything I could about this problem. I eventually found something that told me some information that allowed me to start eliminating some numbers, and then I eliminated everything but the 7 and solved from there. Let's do a couple more examples. Okay, here's the second example, and at first this problem actually seems really daunting. When I first saw it, I was like, okay, where do we even begin? But again, let's start with some observations. This actually ends up being a pretty easy problem, and I'll show you how. So first I see that there's a remainder here. So whenever you see a fraction as part of the quotient, that means there's a remainder. So this single digit number here is going to be half of this 2-digit number here. I was going to put a 1 here and a 2 here, but then I realized this is a 2-digit number. So the possible options for this number and this number, which were made into a fraction and then reduced to 1/2, are going to be 5/10, 6/12, 7/14, 8/16, and 9/18. So we have a single digit number on top that is exactly half of the 2-digit number that goes on bottom. That's how we make fractions as a part of a quotient. It's the remainder over the divisor right here. Okay, so we've at least eliminated everything except for 5 possible options. That doesn't get us very far though. The other thing I noticed is, again, I have a 3-digit number here and a 2-digit number here. And then I thought, well, I wonder what 2-digit numbers multiplied by 91 would result in a 3-digit number. There probably aren't very many options. So I took 91 and I thought, well, let's just start with 10. Okay, so obviously 91 times 10 is going to be 910. 910 would work here. That's a 3-digit number. What if I said 91 times 11 though? I bet we're going to be over 1,000 now. So we take 91 times 1 is 91. 91 times 1 again is 91. I add those two together, and sure enough, I get a number that is over 1,000. So that's a 4-digit number, which means that number can't fit right here. So what I'm doing is I'm taking the divisor, multiplying it by the quotient to try to get back to this dividend right here. So that means that this number right here cannot be an 11. It's a 2-digit number that can't be 11 or higher. Anything higher than 11 is going to result in a 4-digit number. So this has to be a 10. So now I've got this answer right here. Once I have these two numbers here, I simply multiply them together and I get this number. So 91.5 times 10, I can take 91 times 10 to get 910. I can also take 1/2 times 10 and get 5 and add the 5 to the 910 and I get 915. So now to double check that we have the right answer, we can actually work this problem out. So 10 goes into 91 9 times. 9 times 10 is 90. Subtract, and we end up with a 1 here and a 5 here. 10 goes into 15 one time. 1 times 10 is 10. We subtract and we get a 5, and then 5 over 10 ends up being this fraction here, reduced. So that's the correct answer. So you can see it looked pretty daunting at first, but once we realized, wait a minute, we have a 2-digit number times a 2-digit number times 91, actually 91.5, that has to equal a 3-digit number. There was only one possible 2-digit number that could go here to multiply by this number that would end up with a 3-digit number. So that's how I solved that one. Okay, let's do one more. This one's just a bit trickier, but will be a good one for us to go over. So the first thing I noticed as I observed the different numbers and blanks on this problem is that I know that this is a 9, right? Because 9 plus nothing is going to be 9. Okay, so that's kind of a given, and that's helpful. I also know that 3 plus whatever number is here is going to be a 9, so this has to be either a 5 or a 6. So one thing I'll do is I'll actually write a little 5 and a little 6 here. And what I'm saying to myself is I know this number either has to be a 5 or a 6. If it's a 6, then 3 plus 6 is 9. If it's a 5, that means I have an extra little 1 here that I'm borrowing from this column right here. This number would be more than 9, it'd be 10 or higher, and I'd be putting that 1 up here. 1, 3, and 5 is 9. So this has to be a 5 or 6. That's good to know. The next thing I notice is that this number right here, this digit, plus this single digit have to multiply together and have a 9 in the ones column. Now, as I start thinking about what numbers can multiply out to have a 9 in the ones column, I think about 9, 19, 29, and I just work through all the numbers that end in a 9 that can also have, oops, that should be 9, that can also have factors that are single digits, right? So 79, 89, 99. Now 99 I can make with 9 times 11, but 11 is not a single digit number, so I'm going to eliminate that one. So here I know I've got 3 times 3 makes 9. I don't think there's anything here or here. This is, I could think of 13 times 3, but 13 is not a single digit number. 49 has factors of 7 and 7. Those are both single digit numbers. 59 is a prime number. 69 doesn't have any single digit factors, and so you can see I start eliminating all these. There are only actually 2 numbers that end in 9 that have 2 single digit factors. So I put a little 3 and a 7 here because this has to be either 3 times 3 or 7 times 7. Now at this point I actually don't know which one to use, the 3s or the 7s. It's either going to be 9 or 49. So I just have to pick one, and sometimes with these problem solving kinds of missing digit problems you have 2 options or even 3 options, and you just have to pick one and go for it and see if it works, and then sometimes you have to erase a few numbers. So let's try that. We're going to pick the 3 and the 3 first. So let's do 3 times 3. Now 3 times 3 does give us 9. That's why we have that 9 there. 3 times 3 then would put a 9 here. And then 3 times a single digit number here would have to give us a 3 and another digit. Now there isn't a single digit number that I could put here and multiply times 3 that would give me a 3 in the tens column, right? The biggest number I could put here is a 9. 9 times 3 is 27. That's too small of a number to have a 3 in the tens digit, which means that the 3 basically isn't working here. The 3 times the 3 isn't working. I actually need a bigger number here. So I'm going to erase the last couple of things I wrote. That is a little frustrating to have to erase things, but now I know it can't be 3 times 3. That leaves me with just one possibility. So now I know this has to be a 7 times a 7. So now I've got 2 more of my blanks filled out, which is great. I can work a little bit more of the problem now. 7 times 7 is 49. So I put the 4 up here. 7 times 3 is 21, plus 4 is 25. So I can put a 5 here and a 2 here. And then I've got 7 times some number plus 2 is going to give me a 3 and another digit here. Now how am I going to figure out this number right here? Well, I can at least eliminate some numbers and figure out what the options are. So I need 7 times a number plus 2, and it needs to end up being 30 something, right? 33 plus another digit here. So 7 times 4 would be 28, plus the 2 would be 30, so 4 would work. 7 times 5 would give me 35, plus the 2 here would be 37, so 5 would work. But 7 times 6 would be 42, plus the 2 would be 44, so it can't be 6, can't be more than 6, obviously. It also can't be lower than 4, because that would give me a number that's less than 30. So my possible options here are 4 and 5. I'm going to put a little 4 and a 5 here. Okay, now I'm going to try to work on this number right here. This is where our observations come into play again. We have a 3-digit product here. So this single-digit number here multiplied by this 3-digit number ends up with a 3-digit number. So the only possible values that could go here are a 1 or a 2. And the reason is, if I had 437 right here, if this ends up being a 4, I could multiply it by 1, or I could multiply it by 2 and have a 3-digit number, have something that's less than 1,000. If I had a 5 here, 537, the only number I could multiply this by would be a 1 and have something that's a 3-digit number. So I either have a 4 or 5 here, which means I have to have either a 1 or a 2 here, right? Now if I have a 2 here, and I multiply that by 7, I'm going to get 14. I'm going to have an extra little 1 up here. But then when I multiply the 2 times the 3, that gives me a 6, plus the 1 is 7. And they've given me a 3 here. So that can't be true. This has to be a 1. The only possibility is this has to be a 1. Which means I could fill out some more blanks. I have 1 times 7 is 7. 1 times 3 is 3. They've already given me that. Now I have 1 times either 4 or 5 here. I've already decided this has to be a 5 or a 6. So 1 times 5 is the only value that fits there, right? It can't be a 4 because this has to be a 5 or a 6. So now I've got almost all of my blanks filled out. I can add the 5 and the 7 together to get 12. I put a 1 up here, and now I have 1 plus something plus 3 equals this digit right here. Because I have 537 here, I know this has to be 537 times 1. So I can fill out this blank right here. 7 times 5 is 35, plus the 2 is 37. That has to be a 7, which makes sense because we know this has to add up to at least a 10 in order for us to have a little 1 here to add these up to 9. So 1 plus 7 plus 3 is 11. I put the little 1 up here. 1 plus 3 plus 5 is 9. Okay, so that was definitely one of the harder ones in the book that I've seen. There were a lot of different pieces to figuring that one out. And the book, in the solutions menu, will kind of explain some of the steps that they take. Of course, it's not always very thorough, but that kind of walks you through how I would have solved that problem. It would have taken me a while. This is not an easy one. And again, just a combination of observing different things that you notice about it, taking step by step, and sometimes just guessing, saying, you know, I know this is either a 3 and a 3 or a 7 and a 7, and just going one direction and seeing if you get it right, and then having to erase some numbers sometimes. So anyway, I hope that video was helpful, and that's all I've got.